Hello everyone, we'll be talking about the Micro PIV technique, and we will discuss the basic principles of PIV and Micro PIV technique and how it varies with the PTV technique, particle tracking velocimetry, and we will also talk about the issues related to such kind of systems and how to troubleshoot some general problems. So basically the overall idea is to give an overview of this technique. So why do we actually need a technique which helps us to visualize any kind of a flow? So basically what I mean to say is, basically you have air all around you and you also deal with water everywhere, but we cannot see it. So basically if you are saying some things, for say if I am saying something, I am blowing a lot of air around me, but how do we visualize that? As fluid dynamists, we are very concerned with the fluid properties and how basically the forces and those kind of things play a role in changing their structures and their properties. So that is why we want techniques which can help us to find the various flow parameters like the pressure, temperature and those kind of things. So basically I'll show you some videos where you can see how we can visualize air. So here you can see we are blowing air jet, and you can see we are able to visualize this jet very well, and you can see the flow around it also, which is actually getting sucked in because of this high velocity jet. Now we are using olive oil droplets of almost micron size to visualize this. However, and also actually we are illuminating it with a green light laser, which is very high power and high intensity source of light. Now once we off this light and we don't seed this air with olive oil droplets, then also we will be able to generate these jets, high speed jets and low speed jets, but we won't be able to see it. So it is very important to seed it and those kind of things. So for this is just a trial video, and using this video actually you can extract the characteristics of such kind of flows. And inside water, so I'll show you some more images. So here you can see some underwater visualization of nothing but just the water. So what we did was we took some rhodamine, which is a fluorescence material, and we basically we made the laser light to fall on it, and you can see these standing structures of vortices which is actually underwater. So basically this is a tank, and everything is happening inside this tank, and mind you this is at very low time scales. So basically these are standing structures which actually keeps forming inside any kind of a water pool. So visualizing this is really important for us as engineers and as fluid engineers basically. And so PIV is one of such techniques which actually helps us to visualize as well as take out quantifiable data from that visualization, which can be used to basically calculate a lot of things. So determining the velocity of fluids, as we saw now, is not as straightforward as solids, because with solids you can very easily like track a solid and at large scales basically. So if you have a ball of 1 centimeter or say 10 centimeter 20 centimeter size, you can easily see it and visualize it, and you can reveal the velocity in many ways. However, this is not the case with fluids, because by fluids I mean gases and liquids, because we cannot actually distinguish the molecules very easily using our naked eyes. So we need some techniques. So there are a lot of techniques. A few of the indirect techniques of measuring the velocity of fluids are like pressure probes, anemometers, hot wires, etc. Like pressure probes are very widely used. These are based on mostly Bernoulli's principle, and however they are cheaper. They can lead to large measurement errors because most of them are actually intrusive in nature. So what I mean by intrusive here is, so you have a flow field and then you have to put something inside that flow field at a single point actually, and that will respond to the changes in the fluid that is happening, and using some kind of and it will generate some kind of signals, and those signals will be then used by by you or us to get the quantifiable data. So basically one of the other problems is it is only giving you velocities or other parameters at a single location, which is mostly not desirable for us. Now optical techniques like what we are talking about is like PIV, PTV. They are very costly but can give you very accurate results, and also it gives you a comprehensive result of the flow field. Basically if you have a flow inside a channel, so using an optical technique like the laser which I showed you initially, it actually enlightens the whole region from where you can extract data now, unlike the other indirect techniques. And as said, I mean, these PIV and PTVs are mostly non-intrusive in nature, well, at least compared to the other techniques. Yeah. So Micro PIV stands for microparticle image velocimetry, and the idea of Micro PIV actually comes from the macro PIVs, which you have already been introduced in the previous lectures by Professor Basu. So basically the main idea and intuition behind the whole technique remains quite similar, other than the fact that now we are dealing with very small systems which are of micron size, and here the problems are pretty unique compared to the problems we face during macro PIV systems, where the systems are mostly at larger scales, and the setup, which is basically the usage of camera and lenses and laser, becomes a bit different in case of Micro PIV compared to how it is set up in macro PIV. However, again, the basic idea of finding the flow field remains, finding a quantifiable flow field remains pretty similar. So now let's see why we actually perform PIV as discussed in details in the previous slides. Basically we need to find the velocity field of different kinds of flow configurations, and that's why we do PIV. And when the same is done for micro scale geometries, we name it as Micro PIV. Simple as that. So now here you can see there is a channel, and inside that you see some vectors. So this is basically a typical PIV output, basically you can say. So suppose you have this channel which is of micron size, you can imagine, and now you have C-rated particles, and when you image it and do the Micro PIV process, you get something like this. Now what are these? You can see you see very regularly spaced vectors, which are velocity vectors obviously, and you have resolved this whole section using 4 vectors, and then again here you can see they are converging, and then you see 2 vectors resolving this region. So basically this is what you get from an output of the PIV. So here you have basically at each location, you in the flow field, this channel, you have the x and y component of the velocities. For instance, you can, if you talk about this vector here, you don't see any y component, so there is just a straight vector in x direction. However, here you can see this vector starts to incline in this way, so you have some x component and you also have some y component. So if you decompose this vector, you will get 2 velocities, right? And again here you see something very straight. So now you have the velocity data of this flow field. So now you have everything. Basically using this velocity data, you can find quantities of need like kinetic energy, vorticity fields, which are very important normally, stress fields, and also the pressure field can be derived using the velocity fields by putting it in the Navier-Stokes equation. And yeah, so basically if you have the velocity field, you have everything, and that is what we need from a PIV data. So here you can see a micro PIV setup from LaVision and our lab. So I'll just briefly go through the components, and we'll be discussing it in a bit more details in the later slides. So here you can see this gray box is the PIV laser, and this laser actually comes through this attachment and it comes inside here, and basically this is a dichroic mirror, and this laser actually gets reflected and goes back on top. Now what do we have on top is basically here you'll have an objective, microscopic objective, and this is the sample which you want to visualize. Here you can see a small spot here, and that is basically a droplet, and it has some fluorescence particles inside it. Now when this laser actually comes here and goes up, this fluorescence particle will emit light of the required wavelength, basically whatever it is made to do. So here if it's a green light, it actually emits the red light, and basically it comes here, and because it's a dichroic mirror, it will actually reflect it will reflect back, and there is an arrangement which actually reflects that emitted light at this angle, this side, and you have a camera setup here. So for your information, these kind of setups are highly modifiable in nature, and you can change the camera, you can change the laser also, and you can actually make it as an inverted microscope as a whole thing. So yeah, here we are using an imager intenser, as you can see, which actually is suitable to capture low light images. It actually it converts the low level lights to electrons and amplify those electrons to get better images. But yeah, normally high speed cameras are used and those kind of things, and then yeah, you can actually use put a micro channel here, and you can make the flow inside that, and you can record things from bottom. So let's talk about the basic idea behind particle image velocimetry in general. So basically, to visualize any kind of fluid, the fluid can be gas or liquid, both, we use some kind of seeder particles, also known as tracer particles. We put it inside those fluids, and basically that we assume that seeder particle, all the tracer particles, follow the fluid faithfully. So this faithfully term signifies that the particle would not behave differently, and it should actually immediately respond to whatever changes are happening in that fluid. So the use of seeder particle is the most important thing, because that helps you visualize, and the choice of seeder particle is probably the most crucial step in doing PIV. And now what we do, we use we record images at different intervals of time, and then the displacement of a group of particle is calculated using some kind of correlation. So we'll talk about that in later slides, basically. And this delta t, basically the different time intervals, can actually be set according to the time scales of your experiment, and then the displacement is used to calculate the x and y components of the velocity. And as already said, I mean, if you have the x and y velocity with you, you can find almost everything in a flow field that is needed. But again, how is it different from PTV, which stands for particle tracking velocimetry? So now we'll go into PTV briefly. We'll talk about this technique also, because this it's kind of an old school technique, but it's very intuitive, because if you see some particles inside a flow field, your first intuition would tell like, okay, let's track that particle, right? So this is what PTV does actually, right? So that's why I'll just go through it, and it should not be confused with PIV. And so yeah, so in PTV we actually track individual particles inside the flow field. So as you can imagine, I mean, if you have a channel, you put some particles inside those channels, and now you try to track these particles. However, again, these particles should not behave on its own. I mean, it should actually faithfully follow the flow. That then only it will be able to give you accurate data of the flow. So what you do is basically you take single particles as seen here, and you actually start tracking them in time. Okay, so for representative purposes, I'll show. Now let's talk about these three particles. Okay, I mean, you can take single particle also in a window. There is no window as such, but yeah, just for representative purposes I have shown it. Now this three windows looks something like this in time t. After some delta t time, after some time, they have moved to new position inside this window. Okay, let's talk about this window. But in again in practice, you don't need to use such windows and all for PTV normally. Now if you overlap these two windows, you should get something like this, given the fact that these particles don't go out of the window, but yeah, don't consider that for now. So now you can see this particle has moved here, this has come here, and this has come to this side. So now you know the delta t, in what time it has come. So if you consider this particle, you can see it has moved delta x and then it has come delta y. If you resolve the basically this vector, you get delta x and delta y. And then in u direction, you can say the velocity is basically del x by del t, which can be approximated as dx by dt, and also in y direction you can get del y by del t, which is dy by dt. So yeah, so basically what you are doing is you are picking up each particle and tracking it in time. So this dt is delta t is very important, and it should not be very large, or it should not, because if it is very large, then you capture these two images at a very far in a very far time space. Basically, if your particle basically if there is some kind of gradient in the flow or some kind of turbulence, then the particle might get lost during that delta t. So this delta t basically needs to be chosen very carefully depending on the type of the flow you're dealing with. So let's see what are the issues, like the common issues attached with PTV. First thing is many a times these particles can actually become indistinguishable if they are excess in number. So basically so yeah, it's very important to have very less number of particles in the flow field. And also if you use large amount of particle, I mean this large term is very relative, right, because it depends on the channel size, right. So if you are using a large amount of particle compared to what is the width, or like basically what is the volume of your micro channel, it can actually clog it, and that can definitely disrupt fluid flow, because if it clogs your inlet or outlet, there can be high levels of pressure drops, which can actually cause a lot of fluctuation and those kind of things inside your micro channel. So yeah, PTV, yeah, it's very important to keep this in mind. And again, one of the major problems is that basically it is very tough to get regularly spaced vectors, as in case of PIV, because your particles will also be less in number, so you cannot get vectors at every place because the particles are very sparsely arranged, right. So mostly PTV is very desirable when you deal with live organisms like bacteria, or at those scales where you are actually tracking a single cell rather than finding the flow field of a system, like flow inside a channel, or basically flow inside a micro channel and those kind of things. So this technique is normally used when you are actually tracking the motion of a bacteria or other kind of organisms. I'll briefly talk about PTV algorithm, not exactly algorithm, but some of the scenarios we face while basically doing PTV. So PTV depends a lot on the method of imaging. So basically different images, different types of imaging basically can have different intensity profiles across the particles, and the variation of intensity can be very low and high, and there can be a lot of noise in the image. So it's very important to know the intensity variation in your imaging system. Okay, so now let's see some scenario. You have a particle here, and this blue color actually shows the intensity of the particle, and it is actually to be tracked in a flow field that is outside here. And now you can see the intensity inside the particle and outside the particle remains very similar, just that the edges can be actually seen to be very dark. Let's see, this is I1 intensity and inside is also I2, and these two are basically same. So now if you actually draw a line across this center of the particle, so and if you plot the intensity across that line, you will get something like this. So basically you are getting these two peaks, right, and these two peaks are actually the two edges where the line is actually cutting the particle, right. Now if I talk about like this, so it's something like this. Basically, if you have this line here, right, so these two peaks are actually corresponding to this part and this part. Now if there are some noises, which is normally the case, so actually intensity will look something like this. It will vary here also, I'm not making it, and it's here, and again this. So now what you need to do is basically you locate the edges using these peaks, and then you perform some edge detection algorithm, and then if you have the two edges, you can actually fit a circle about it and find the center of the circle. This can actually have some variation, but yeah, this kind of scenario is mostly is kind of rare, and you don't get it often. So normally we deal with this kind of systems where it's kind of a fluorescent imaging, where these particles are very bright, and outside you get a dark field basically. And now for this case, if you actually again same thing, draw something like this, so you actually get something, the intensity profile looks something like this. It's very smooth, and it's kind of, you can use a gauge, and basically it's kind of a Gaussian fit. And if it's an ideal fit, then actually the center of this particle should give you the brightest intensity, basically the pixel at the center should give you the brightest intensity, and you can actually get the center of the particle from this graph, right? And then you can trace this brightest pixel along the flow fit. So yeah, these are the techniques, and there are other techniques like the centroid method, or the intensity weighted centroid, area weighted centroid, and those kind of things, where you can actually which you can use to track particles in PT.